Our project was to build a toy car coil gun. We were to design and build a safe magnetic launcher for matchbox cars at high speeds and then measure the speeds achieved by the final demo day. The main objective of this project was to explore coil gun design and how to properly build a coil gun. The motivation was mainly how cool coil guns were and if we would be able to build one ourselves. The deliverables for this project for Milestone 1 were to finalize the number of coils at max speed, for Milestone 2 to finalize the app GUI design connected to the speedometer, and for the final design requirement 3, the car was supposed to meet an intended speed of 13 miles per hour.
So here's a block diagram that shows how the Android app functions with the Pico. So once the Android app is connected by Bluetooth to the Pico, then the coils can be charged, and there's a button on the Android app that can signal to the Pico to activate all 4 coils and launch the car. Once the car is launched, then there's 2 beam gates that the car has to break to allow the Pico to calculate the speed of the car, which is communicated back to the app in meters per second. And then the car can launch again once the coils are charged.
The initial hardware design requirements of the coil gun were continuously updated and changed throughout the project. For example, our initial design utilized 4 100 microfarad capacitors, whereas in our finalized product used 12 2,000 microfarad capacitors. And we went from 5 feet of track to 12 feet of track once we realized that the car kept moving further and further. But the biggest design requirement that we wanted to implement throughout the project was that the car was going to go at least 21 miles per hour.
The design for our coils evolved over time. Originally, the car was going to pass through the entire coil, but we soon realized that wouldn't be feasible considering how large the air gap would be. We then designed much smaller barrels and used 70 windings with 5 layers for a total of 350 layers on each coil. The coil is sitting on a 3D printed barrel.
The design for the track is just a straight line of 12 feet of your typical orange Hot Wheels track, which is glued to a piece of wood to raise it up so that it is properly aligned with the coils. There is a green 3D printed holder which holds the IR brake beam sensors, which in turn act as the speedometer and is placed at the beginning of the track. And the track design throughout has mainly stayed consistent. We thought about implementing a loop-to-loop if we were able to manage to build up enough speed, but we weren't able to utilize that.
Each coil is connected to a relay which has 3 2,200 microfarad capacitors in parallel, being charged with 60 volts across a 50 ohm, 25 watt resistor with a separate 1K ohm bleed resistor. The capacitors lead into the relay, and the Pico sends a 5 volt signal through the relay to discharge the capacitors.
There weren't many software design requirements for the project, since most of it was based on the design of the circuit and making sure all the coils worked. So we added features such as making an app that could launch the coils from the app, and also having the Pico programmed so that it could calculate the speed of the car using the 2 beam gates. So for the Pico, there are 4 separate pins that are connected to 4 relays that control each of the 4 coils to launch the car. This way we can have delay between when each coil activates, so that when the car passes through each coil it increases in speed. The Pico also needed to be programmed so that it was connected to the 2 beam gates, so that when both beam gates are broken, there's a difference in time calculated between when they're broken. And since we know the distance between these 2 beam gates, then we can calculate the speed of the car between that time. Then there's the Android app, which is connected to the Pico by Bluetooth. The app can launch all of the coils at once, or just a few individual coils at a time. And it can also get the speed of the car that's sent from the Pico and display it on the app.
Now it is time to go over some of the equations that we use to determine the specifications of some of our components used in the coil gun. So first, let's go over the capacitors. So the size capacitors we wanted to use were determined by setting the kinetic energy formula to the stored energy inside of a capacitor, with an additional unit on the capacitor side to signify the energy efficiency. So by plugging in our numbers, so first on the kinetic side, we plug in 35 grams for the weight of the Hot Wheels car, and 4 meters per second, which is roughly around the 20 miles per hour that we specified. And so next, we take our energy by taking 60 volts, and then we're leaving the capacitance there, as in that's what we're trying to solve, and then multiplying the stored energy by 1%, as in that is the efficiency we found most coil guns to be operating at, between 1 and 3%. And so we came out with 1,977 microfarads, and since that is not a standard number, we decided to go with 2,200 microfarads just to give us a little bit more wiggle room. The next component that we're going to go over is the bleed resistor. And the bleed resistor is there to safely discharge the capacitor over time. So this equation is multiplying the capacitance by the change in voltage over the change in time, which by multiplying our 2,200 capacitors by 60 volts, and we want it to discharge roughly around, we want it to be around 90% of its charge in about 2 seconds, which leaves us a amperage of about 0.06. And keep in mind, this current is an estimation due to the nature of how capacitors charge. The current is not going to be the same throughout, just as the voltage is not going to be the same throughout. And so with this, we determined that our bleed resistor needs to be roughly around 1,000 ohms. And this number doesn't need to be completely exact, as in it just needs to drain over time. So as long as it was around 1,000, we are perfectly fine. The next part of the methodology I would like to discuss is the simulation aspect. So it was very difficult to simulate the circuit due to the relay being a part of it, and the circuit components were acting ideally instead of real-world behavior. And what I mean by this is that within our circuit, that the capacitors would charge pretty much instantaneously, and the relay would just not be able to function properly. So we couldn't really model it incredibly well, but we were still able to get some models shown.
To test the time delay, we mainly had to use trial and error after figuring out a general range of time, which landed us in the milliseconds range, starting from one coil and getting it down before moving on to the next in line. As the projectile went through each coil, we noticed less gains over time.
3, 2, 1.
Launching from only the first coil has the car move about 3 to 4 feet at an average speed of about 0.474 meters per second, resulting in an energy transfer of about 0.2% efficiency. Next, launching with the first 2 coils results in a near double increase in distance with 0.657 meters per second speed, giving us an energy transfer efficiency of about 0.55%. When launching the first 3 coils, the car travels between 10.5 to 11 feet, averaging about 0.747 meters per second speed. This gives roughly a 0.7% efficiency for energy transfer, which landed us near our old prototype's final outcome with all 4 coils, marking a huge improvement in the design. Lastly, when launching all 4 coils timed correctly, the car would consistently go beyond 12 feet, which was the distance of our track, at about 1.082 meters per second. This was always our best launch, proving that all 4 coils were correctly synced, and that resulted in an efficiency of over 1%, which is slightly flawed as the car comes to the rest at a much earlier due to falling off the track.
Some of the issues we experienced with this project were burning through components such as our resistors when using high voltage, trying to get enough current through the coils, which resulted in us switching from transistors to relays. Android Studio and other software we were using to make our app were having trouble working properly. The speedometer was sometimes not registering the brake beam, and timing the coils took a lot of trial and error and may not be exact.
There are a couple of future directions that we can take this project if we wanted to continue developing it. The first example is higher wattage resistors, which will help dissipate more power. Throughout the course of the semester, we realized that our resistors would get incredibly hot while repeated use of just having the circuit on or firing the gun. By having these higher wattage resistors, that means we can keep testing and keep firing the gun more and more and lead to less downtime. A second future direction is a heavier, more ferromagnetic projectile with a rounded tip. all of these factors will increase the projectile speed just to having either A, like more pull from the coils, B, more energy in the the kinetic energy equation, or even C, a rounded tip to better break through the air rather than the flat surface that the Allen wrench uses. And lastly, we could also use higher voltage and higher capacitance from the power supply. Just increasing more of these will allow more magnetic force to be generated with the coils or allow more energy to be stored up within the capacitors, which will lead to more energy used in the launch.
In conclusion, the coil gun can be fired successfully at different speeds, using each stage of the coil to vary the speed. The coil gun is able to be fired directly from the app, and the app is able to record the speed. Not reaching the maximum speed of 21 miles per hour with the car is disappointing, but the projectile being launched is able to reach 21 miles per hour, even if the car itself is not. To conclude, this was a fun project, and we managed to complete goals that we as a team are proud of.